Alright, video 1.6 is going to talk about what math you could do with vectors, especially the math we're going to be doing pretty frequently. Here are the most common operators that you will do with vector quantities. You can add vectors, subtract vectors, and decompose vectors, which means breaking them into components. We'll get to that. This video won't touch on this, but you can also multiply vectors by each other or by scalars. And you can do any of these things qualitatively or quantitatively. We'll start qualitatively and we'll look at addition first. Vectors can be translated, which means moved, as long as they stay parallel to themselves. In other words, you just can't turn them, and you also cannot change their length because those are the two things that define a vector, their magnitude, or their length, and their direction. So if those things are unchanged, you can do anything else you want. So here's A and B, and we're going to add them together and see what comes out. First thing to think about is, what does it mean that you can translate a vector parallel to itself? I want to show you. I'm going to move A all over the place, and I could stop anywhere, but I'll stop here. A is still A. As long as it's still pointing up in this example and it's got the same length, which it does, I can put it anywhere. I'm not going to leave A here. We're going to add these tail to tip, so I'm going to move A down to the tip of B. There we go. And let's also just clean this up a little bit because those are getting kind of overlappy. You just start at the tail or the beginning of your first vector and you draw a straight line to the end or the tip of the last vector. It doesn't matter that there's two here, it could be any number of arrows I was adding. You just start at the beginning and you go straight to the end. So there is the answer. We'll call that vector C. C, to use that terminology again, is the resultant of A and B, or we can express this mathematically as A plus B equals C. I hope you now understand that vector addition does not work like algebraic addition, and if you know the rules of triangles a little bit, this should make sense. B and A are about the same length, pretty close, so let's assume they are the same length. So let's call them 1. We'll make the math nice and easy. So what is A plus B? Well, it's 1 plus 1, so that's 2. That would imply, according to this formula, that C, this vector in green, is 2 units long. And clearly that's not the case because the rules of triangles dictate that the third side cannot be longer than the sum of the other two sides, or equal to. You can't make a triangle that way. So this expression must be interpreted in a new sort of way. Because the directions are important with vectors, you can write this equation, but you can't solve it unless you give the direction of each vector. Some of you were probably wondering as you saw that example, why did I put B first and then A started at the end of B? I mean, A precedes B in the alphabet, so why wouldn't that go first? So the question is, can we do it that way? Can we start with A and then add B to A? Can we do the old switcheroo? I want to find out if that's valid. So I'm going to now start with B and move it to the end of A. Again, tail to tip. And then the resultant is from the beginning of A. Here we go. To the end of B, or the tail of A to the tip of B. And there it is. We'll call that C once again. And now for comparison, let's bring back that last image, and you'll notice these C's are identical. You might be looking at this and saying, well, I don't think they are identical. I mean, this first one is visibly lower on the screen, and this one's higher up. But that's okay because of the first thing we talked about. Vectors are the same as long as you don't change their direction or change their length. Both these C's are pointing in the same direction and have the same length or magnitude. Symbolically, A plus B is the same thing as B plus A, or verbally we can say vectors can be added in any order and they give the same answer. Alright, the next thing I want to look at is qualitative vector subtraction. So just like subtraction is the opposite of addition when you're dealing with numbers, vectors work in much the same way. Let me show you an example. What if I want to take one vector pointing up and then subtract from this first vector a second vector pointing down, and it's not as long. In fact, I made these exactly 2 inches long and 1 inch long. Of course, the screen you're looking at might change the size of that. What do you get when you subtract a vector? Subtraction is negative addition. So I'm going to take that away and I'm going to replace it with plus a negative. The only thing that might be confusing here is a negative number is something you understand, but a negative vector is sort of something we have to define. Negating a vector makes it reverse its direction. So it's not going to change the length. It's still going to be 1 inch long, but it's going to have the exact opposite direction, 180 degrees apart. So let's see what that looks like. And now it becomes a really simple problem. You just do tail to tip addition, and if you add these two vectors, since they're in the same direction, I'm going to get two vectors pointing upwards, tail to tip, that are now 3 units long, 3 inches long. And because I do the resultant from the tail of the first to the tip of the last in all cases, every time, the final answer looks like that. That is the resultant of these two subtracted vectors. So what is vector decomposition? Here's the gist. If a vector is not parallel to one of your axes, then you have to break it into components, which show how much of the vector points in the x direction and how much of it points in the y direction. The other thing that's useful to know is this is the undoing of what we just did with vector addition. This is reverse engineering a resultant to get the components or the initial vectors that make it up. So let me show you an example. Take a traditional xy axis as we have here, and I'll put the vector from the last question on this, and it's straight down, 1 inch long, and it's straight down. So do we need to break this into components? The answer is no, because it's already parallel to the y-axis. Components only show you how much of a vector is pointing in a single direction. In other words, how much of this vector is pointing left, or how much of it is pointing right. And since it's straight down, there's none of it pointing left or right, so there are no components. All of it is vertical. Another example, we'll put this one straight to the left in the negative x direction. Once again, you don't need any components because none of this vector is pointing up or down. It's entirely horizontal. Let's now look at an example where you do have to break a vector into components. So we'll make it a diagonal in the sort of positive x, positive y, or northeasterly direction. We'll call it vector v. And what I want to do is explain how components are determined. Each one of them, like it says up here, is parallel to an axis. So what I want you to do when you have to break up a vector is I want you to put your pencil down on an axis. It doesn't matter which one. I'm going to choose y, and I can't show you a pencil on the screen here, so I'm going to put a black line on the y-axis. We do need components, like it says. What we're going to do then is we're going to keep our pencil vertical or parallel to the y-axis, but we're going to move it in the opposite dimension. So since this is a vertical line, I'm going to move it horizontally, and I'm going to move it until it is at the end of the vector. I'll show you what I mean. So now we know how far the vector points only to the right. The other thing that's useful about this, now that we have this line over at the end of the vector, or at the tip, we can draw our first component. Components are always drawn using dotted lines, which means this is not a full vector, this is part of a larger vector, and it starts at the tail and goes along an axis until it hits the line that we just shifted. So here is the horizontal or x component of vector v. The other thing that's useful about this black line or your pencil is it shows you, after you draw the first component, it shows you where to draw the second one. It's directly along the line, and it will always connect the tips of the resultant and the first component. So these two arrowheads, we need to draw a straight vertical line between them, and there it is. Finally, in terms of nomenclature, we just name them the vector, whatever it's called, with a subscript that denotes the dimension. So for instance, this first one we drew, it's parallel to the x-axis, so it's v subscript x, or we'll say v sub x, and then the other one is v sub y, meaning literally the amount of v acting in the x direction and the amount of v acting in the y direction. The last thing to talk about is the part that students have always had trouble with since I've been teaching this subject, and I've come up with a way that I hope is going to make this a little bit easier for you, and that's why we just did the thing with the pencil, because that might have seemed kind of obvious to some of you, especially if you already know about vectors. But that pencil trick is really going to help with what we're about to do. So here's the gist. We don't always use this xy axis, this horizontal vertical axis. We often have to change the axis by tilting it, and a really common example of when you'd want to do this is if you do a ramp question. So let's say something is sliding up or down a ramp. It's not moving horizontally or vertically, I mean only horizontally or vertically, but it is moving in a straight line. So it simplifies our analysis a great deal if we can make all of the motion one-dimensional. And to do that, we're going to have to change this reference frame. So to summarize, axes are not always horizontal/vertical, but they are always perpendicular to each other. And the rules I just taught you with the pencil, those are still going to work, and I want to show you how. So here's an example of where you'd want to use a tilted reference frame. And if you want to envision what's happening here, the x-axis is the surface of a ramp. So all of the motion as something goes up a ramp or down a ramp is along the x-axis. The y-axis, therefore, is perpendicular to, or we can use the synonym of perpendicular, normal to the ramp surface. Now, let's imagine you're trying to analyze the gravitational force. We know that the gravitational force on any object points straight down. So here's a gravitational force vector. Now, where this becomes kind of interesting is we can no longer decompose this into a horizontal and a vertical component. So if this same vector had been on the first axis I showed you, where it was normal, like horizontal and vertical, you wouldn't have had to decompose this at all. This would have already been along the y-axis. But you can see that's no longer true. So now is where the pencil trick really helps. Here's my pencil. I'm going to put it on the x-axis because we did y last time. And I want to shift it by moving it along the opposite axis. So in this case, y. I'm going to move it in the negative y direction because that's the way the vector points. Here I go, and stop there. And that is where we know one of the two components is going to be. It's going to be parallel to the x-axis, which my pencil still is, and it's going to end where the resultant ends, where this force vector ends. So we always draw the other vector first. So since we drew this pencil, well, I drew a black line, you placed a pencil. Since your pencil started on the x-axis, you're going to draw the y component first. So always start at the origin and go along the axis that you want to analyze. So like I just said, the y-axis, and keep going, keep going, keep going, keep going, keep going, until you hit that line, or your pencil. So that is the y component of this force. Then we just draw the line connecting the two tips, and that is the x component of the force. So you guys remember how before, when we drew the two components that were horizontal and vertical, they made a right angle? And that was because they were parallel to the x and the y axes, which are perpendicular to each other. Same thing is true here. It doesn't matter that they're tilted. I mean, the x-axis and the y-axis are still perpendicular to each other. By definition, they have to be. They always are. So two lines that are parallel to the x, this one, and parallel to the y axes are also perpendicular. So we get a right triangle every time we do this process, and that'll be really useful once we start to do it quantitatively. To label this, finally, we get force of gravity, that's the resultant, or sort of the total force, and then the components of the gravitational force acting in the x and y dimensions are given by force of gravity x and force of gravity y. That is it. I do want to remind you that there is no quiz to take online, but you will be able to take any notes you need to on these quizzes and bring them to class. We'll take the quizzes over these videos on paper, and you may refer to anything that you've written down while we do that.